I'm going to stop my share. You can actually put your slides up, and then as soon as Bill lets us know he's ready, we'll get started, and I'll introduce you.
See, there's 28 participants. Yeah, so I want to mute our audio.
Yep.
Where's the participant?
Okay, super. Perfect. Okay, and you, Vic, you've got yourself muted. If you want to unmute yourself. Yeah, I can. There, I just.
Can you hear me?
I can hear you now. All good. So are people basically set? Bill, how are you doing? Are you ready to go? Awesome. Well, anyhow, welcome everyone. We're really glad to have you here. This has turned out to be a lot of fun and work surprisingly well. And we're really excited to have Vic Reiner here with us today. So Vic got his PhD in 1990 at MIT. He was a student of Richard Stanley, and he's been at the University of Minnesota Twin Cities ever since. He's interested in algebraic, geometric, and topological combinatorics. We'll see some of that today, although mostly he likes to count things. So recently his interests have circled back to one of his first loves, invariant theory and finite groups, particularly reflection groups. He does a ton of editorial work on the editorial boards of JCTA, Algebra and Number Theory, and the new Fair Open Access Journal of Algebraic Combinatorics. He's also mentored just an astonishing number of students, well over 100, ranging from undergraduates through postdocs.
There's a new journal so like the quit.
One of the wonderful things about hosting is that Bill and I get kind of sneak previews of presenters' slides, and this is going to be just a wonderful talk. I hope you all enjoy it. Thank you so much, Vic. Take it away.
Okay. Well, thanks, Joe. I really want to thank both Bill Martin and Joe Ellis Monahan for inviting me here. I wish I could provide you with my usual voice. I'm a bit hoarse today, but Bill and Joe can tell you that yesterday I sounded worse. Anyway, it's a huge honor to give this virtual Combinatorics Colloquium, and I'm really honored to be considered somebody in the Northeast. You know, I come from the Northeast originally, but now I think of myself as in the upper Midwest. So it's good to return virtually anyway. So yeah, I'm going to be telling you about some counting things. My title is Cyclic, Sieving, Old and New, and this is a topic that I and some of my colleagues here at Minnesota, Dennis White, Dennis Stanton, have been involved with for about 15 years almost. And let me just move to my outline. I'm going to tell you what is cyclic sieving. What do I mean? So the definition. And once we've gotten past that, I'm going to just do a bunch of examples. And some of them are going to be old examples, but they have a dual purpose. The first one I'm going to show you is an old example that I think is beautiful, but it's really annoying. And it's annoying because even though it's an example of what we're talking about, I feel like we don't understand it. And the more I advertise it, the more it might reach somebody who's thought about these things, which are alternating sign matrices. I'll then move on to another old example, polygon triangulations, one of our first, which again has an annoying feature. We feel like we don't understand it, and I'm pretty sure it's related to clusters. So this is trying to reach out to the cluster people and get your help to help us understand this. And I won't just talk about old examples. I'll move on to a couple of new examples, or an old example with a new twist. Let me try to annotate here. I should be pointing. Yes. Spotlight. Here we go. I should be pointing to number 4, the old example with a new twist, which will involve necklaces, and it's something that one of my students, Eric Stuckey, has been working on. And if we have time, I'll talk about another newish example. It's one that's at least, it's about a year old. And for those who were at FIPSAC last year, they may have heard Theo Duvropoulos talk about it. But for others, it may be new. So it's one that's joined my list of favorites. As I said on my poster, there's new examples that show up all the time. And I think, oh, that's a nice one. So I wanted to tell you about it. Okay. Any questions before we head on? Good. Yes. Are we advancing? No, I have to stop annotating to advance. Is that right? Stop annotating, advance. There we go. Okay. So in telling you about what is cyclic sieving, I might fail completely. And if I don't get it across, then I'm going to recommend that you look at one of these surveys about it. There's several nice surveys. Bruce Sagan wrote a beautiful survey. I didn't put the title of any of these, but you've got the authors and the year, and they all have cyclic sieving in the title, so you can easily find them. Bruce is in Surveys in Combinatorics. There's another very nice survey. It's a little bit harder to get access to. It's in basically like the Italian Math Society's surveys. It's by Giovanni Gaifi and Alessandro Iraci. That was in 2017. And then, of course, there's 2 things that the Dennises and I, Dennis Stan and Dennis White and I wrote. One was a notices article that was called What is Cyclic Sieving? So it's short. That was in 2014. And then our original paper from 2004 just has a lot of examples in it and is a good. So consult those if I fail here. Okay. Let's see. I can't advance slides without turning off the annotation. Let me do that. So the definition is from this 2004 paper that Dennis's and I wrote. It says, if we're given X, a finite set, we're thinking some set of combinatorial objects, and they're permuted by a cyclic group. So just think there's a cyclic group acting on them, permuting them. And there's a polynomial, x of q, that I think of as some q analog for the cardinality of the set x. Then I'm going to say that this setup, this triple of x with the cyclic action of group C and this polynomial x of q exhibits the cyclic sieving phenomenon if for every d, when you take one of the elements of that cyclic group, so I named the generators of the cyclic group or generators little c. So the elements of the cyclic group are all the powers c to the d. And if I want to know how many elements of x are fixed by a certain power c to the d of the generator, all I do is I go over to the polynomial, this q analog, x of q, and I plug in a complex root of unity, zeta to the d, that has exactly the same multiplicative order as the elements of my cyclic group. So the way you want to think of this is you've got your set X and it has some cyclic symmetry. Some elements have no symmetry, they're asymmetric. Some of them have more symmetry, 2-fold symmetry, 3-fold symmetry. If you want to count how many elements have a certain amount of symmetry, you just plug in a root of unity into that generating function, into the q count x of q. So I think of the x of q as hiding the information about the cyclic symmetry or about the cyclic orbit structure in this action. Okay. And oof, I have to remember to unannotate each time. Good. So we had discussed this in this paper from 2004, but there was a precursor, a very interesting thing that John Stembridge had talked about called the q equals -1 phenomenon. And that's just the case when your cyclic group has order 2. So there's an involution, little c. So c squared is equal to 1. And it's acting on your set. You have some order 2 symmetry on your set. And Stembridge back in 94 would say that you had a q equals -1 phenomenon if you had a q analog x of q such that when you plug in q equals 1, it gives you the size of the set x. And when you plug in q equals -1, it gives you the number of elements fixed by that element, that involution. Okay, and it's exactly our setting when it's a cyclic group of order 2. So some of the examples that I'll show you have that kind of a order 2 cyclic sieving phenomenon happening. Okay. So let's begin with the first real example here, having to do with alternating sign matrices. Are there any questions though before we move on? Okay. So this alternating sign matrices, these have a beautiful, illustrious history. They're explained beautifully in the book by David Brissoon on proofs and confirmations. So they were defined in 1982 by Mills, Robbins, and Rumsey. And an n-by-n alternating sign matrix, it has entries that are 0, +1, and -1. And the entries in each row and in each column, when you look at the non-zero entries, they have to alternate in sign. So they have to start with a plus somewhere in the row, then followed by a minus, plus, minus. It might be that there's only a single plus in the row, but if there's minuses, then they alternate with pluses, and it sums to +1 across each row and down each column. So that means it has to start with a +1 and end with a +1. So here's an example of a 6x6 alternating sign matrix that I've shown for you. And I'm going to call ASM sub n is the set of all n-by-n alternating sign matrices. That's going to be one of my combinatorial sets X. And let's say I wrote here at the bottom that the alternating sign matrices, they're in many ways, they beautifully generalize permutation matrices. So we should think of them as some more exotic form of permutation matrices. Okay. And so stop annotating. Yes. Oh, yes. Right. So what's the cyclic action on the alternating sign matrices? It's a relatively small cyclic group, and it's rotations by 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So the fourfold rotations gives us a little cyclic group of order 4. It's not hard to see from the definition that will take an alternating sign matrix to another alternating sign matrix. And I've shown you for the alternating sign matrices of size 3 what this cyclic orbit structure looks like. You get just a point. You get an orbit of size 4, so that's what I would call a free orbit, an orbit in which the size of the orbit is the same as the size of the cyclic group. There's no stabilizer. You get an orbit of size 2, so these two alternating sign matrices have a twofold symmetry. They're symmetric under a 180-degree rotation. And there's one orbit of size 1. This is the only alternating sign matrix which isn't a permutation matrix when you're looking at 3x3s. And it has a lot of symmetry, therefore. It's fixed under 90-degree rotation, 180-degree rotation, and so on. Okay? So we want a cyclic sieving phenomenon to predict this sort of information. How many of the matrices will be fixed under 90 degrees, 180 degrees, and 270-degree rotation. And so we do have such a thing. And that is, yes, stop. Oh, sorry. First I have to tell you that we do know how to count the alternating sign matrices, and it wasn't easy. So how many alternating sign matrices are there of size n? There's a famous theorem that was conjectured by Mills, Robbins, and Rumsey in 1982 that the number of alternating sign matrices is some product of factorials over another product of factorials with equally many terms on the top and bottom. And the factorials go 1 factorial, 4 factorial, 7 factorial, so they jump by 3 on the top, and they start with n factorial, n plus 1 factorial, and go by 1 on the bottom. And it took a while to prove. Doron Seilberger gave the first proof in 1992, and then Greg Kuperberg came back and gave a different proof that connected it with statistical mechanics and physics. And it's a beautiful story that I highly recommend reading David Brissoon's book about this. But then beyond that story, we could ask this question I was just asking, which is, how many of these alternating sign matrices are fixed under 180-degree rotation? They're called half-turn symmetric ASMs. And how many are fixed under 90-degree rotation? Those are usually called quarter-turn symmetric ASMs. And there were formulas in the literature given by Kuperberg and by Razumov and Stroganov dealing with various cases of what n was modulo 4. The formulas will depend upon the congruence class of the size of the matrix mod 4. And I'm not telling you those formulas on purpose because I don't need to. That's the point of the cyclic sieving phenomenon here. So there's a theorem that was checked by Dennis Stanton in 2004. It's essentially unpublished, and I'll explain why in a moment. He checked that if you look at X being the n by n alternating sign matrices, C is this fourfold cyclic group, or this cyclic group of order 4 acting by rotations, and we take we take this Q analog here. X of Q is some way of turning those factorials into Q factorials. Some Q analog of the factorials is what you do to get your Q analog in this case. So in some sense, one of the most naive things that people ever do when they're trying to produce Q analogs. I take n factorial sub Q, and it's this, I'm defining it down here as 1 sub Q times 2 sub Q times 3 sub Q dot 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 times n sub Q, where each of those terms I now have to define. The n sub Q is a Q analog of the number n, and it's just the geometric series, 1 plus Q squared up to Q to the n minus 1. So when Q goes to 1, this thing will turn into n. And if you like, you can see how to write it as a rational function. It's Q to the n minus 1 divided by Q minus 1. The point of writing it as a rational function here is that it shows that this expression up here, this x of Q, it looks a priori like it might only be a rational function in Q, a polynomial in Q divided by a polynomial, but it will cancel. I'll explain why we know that later on. And if you go back to the beginning where I was defining the CSP, I actually asked that the Q analog should be a polynomial in Q, and this one is. Let me, I'm annotating, so can't go back, but that's all right. This thing is a polynomial in Q. All right, let's not annotate. So what does Stanton's theorem say for the 3x3s? How does it predict that orbit structure that we were talking about? Here's, again, the picture of the orbits. These 7 ASMs of size 3 that come in these 3 orbits. So what the cyclic sieving phenomenon, the CSP here should be saying, is that I take this polynomial in Q. Notice I've actually written it out here, what those Q factorials were, what the quotient is. It cancels down to this quotient of Q numbers, but then that actually does cancel down to a polynomial in Q of degree 8 in this case. And so it's no surprise that when we plug in Q equals 1, we should be getting back the size of the set X. In terms of the way the CSP has been phrased, that's saying when we plug in zeta to the 0, so our 4th root of unity in this case, the cyclic group had order 4, so I should always be plugging in 4th roots of unity. And if I plug in the 4th root of unity that's zeta to the 0, namely 1, I should just get the number of things that are fixed by the identity element of the cyclic action, which is just the size of the set X. So I do get 7. This polynomial has 7 terms, and so I get the 7 elements, and I should be annotating. Let's annotate here. So when I plug into this polynomial, which has 7 terms, Q equals 1, which is zeta to the 0, I get 7, which is just counting all 7 elements of my set X. And that always happens, and it was no surprise in this case. But what's non-trivial here is that if I want to know how many elements are fixed by the twofold symmetry, I should plug in the power of zeta, zeta squared, which has multiplicative order 2. So that's Q equals -1. And if you plug in Q equals -1 here, you can quickly see you're going to get 3. You'll have, what is it? How many terms are even? There's 4 even terms minus 2 odd terms. No, that can't be right. 5 even terms minus 2 odd terms. It gives 3. So the point is that 3 is counting these 3 alternating sign matrices, which are fixed under 180-degree rotation. And then the last one is for the quarter turn ASMs. I should plug in a root of unity, zeta in this case, which is e to the 2 pi I over 4. So it's just I. and I should plug in that root of unity that has order 4, and it counts the alternating sign matrices that have 4-fold symmetry. And there's only one of them, namely this one here. Okay? So any questions about what the CSP is asserting? It's asserting that this will always happen when we plug in these roots of unities in roots of unity into this x of q here as it gets larger.
Could I ask a quick question?
Yes.
Do we know anything about, so for example, you've got some cancellation there in the q equals -1. You're going back to the q equals -1 phenomenon. Can we assert anything about the number of pairs that cancel? Is there a combinatorial statement about those?
Well, somehow that when you say pairs, do you mean numerator and, oh no, you mean pairs within the set.
Yeah, pairs of 1 and -1 canceled out, and then you got what was left, which survived, which counted the objects that are being counted by the CSP. Then you had a certain amount of cancellation. The question is, do we know anything about the amount of cancellation that went there? Does that say something about the object?
Right. I'm trying to understand, when you say cancellation, do you mean additively these powers of Q, or do you mean cancellation of numerator and denominator? Which do you mean?
I mean canceling in the powers of Q. You had pairs of 1 and -1, which when you add them went away. And the survivors and +1s got you your...
Right. Okay. So I think that, I mean, basically we can just, I think I can't say anything non-trivial. In other words, just based on how many things survive, we know how many pairs cancel. In other words, we could subtract off the ones that didn't cancel and divide by 2. So I don't think I have a non-trivial answer for you on that. Is that okay?
Yes, thanks.
Okay. All right. So I forgot to tell you something that's not annoying here. Let me, before I tell you what's annoying about this one. One of the nice things about having a CSP, even if we don't think we understand why it happened, is that you'll notice it's easy for me to remember the formula x of q. Let me be pointing at things again. And so this formula x of q, whoa, let me be pointing and not drawing, yes. This x of q, it's just as easy for me to remember that formula as it was to remember the original Mills-Robbins-Rumsey conjecture formula. And once you have it, these root of unity evaluations, if it's a product formula, your x of q, they're incredibly easy to do. So, of course, the q equals 1 is just the same as the original. You just take all the terms on top and cancel with terms on the bottom. When you plug in the q equals -1, essentially what you have to do is you look at like these 7, 6, 3, 2. You ignore the terms that are not divisible by 2 in the numerator and denominator. They tend to match up according to being in the same residue class, mod 2. In other words, in this case, the odd terms match up in numerator and denominator. You just forget about those. And then when you had even terms like 6 and 2, you just divide them through 6 over 2. So this is how you do the q equals -1 evaluation. And when you have product formulas, it always works like that. For example, this q equals I, it's not illustrated so well, but none of the terms in the numerator or in the denominator were actually divisible by 4. None of them were congruent to 0 mod 4. They all had residues which were either 2 mod 4 or 3 mod 4, and those you just cancel down to 1s. So when you have these nice q formulas which are products, actually getting the formulas that Razumov and Stroganov and Kuperberg had written in their papers are incredibly easy to derive from the q formula. You really don't have to do any work at all. So that's a good thing about knowing that the CSP exists. The bad thing, though, what's annoying here, I'm about to tell you, is the proof, and that is it's brute force. As I said, we know how to easily do the evaluations of that product formula at 1, -1, and plus or minus I. And we had the answers already from Kuperberg and from Razumov and Stroganov. And so what Dennis did is he sat down and compared them and checked, yes, they were the same. I'm not trying to malign Dennis. He would admit that this is why this is not a published paper of Dennis Stan. This is just, something it's in an REU report. In fact, he had REUs, make sure that he hadn't made any mistakes in his check. So it would be nicer to have an insightful proof here. And so if I'm going to be complaining to you all the time about what's annoying, I should really tell you what it is that I want. And so I'd like to tell you what I mean by a good proof. Okay? Any questions before I show you what I mean by a good proof? All right. What I like better. A trace comparison proof. This is my favorite. What I'd really like to have explaining a CSP in each case is a complex vector space. All right, let me be annotating. I would like to have a complex vector space V with two different bases for that vector space, both of which are indexed by my combinatorial set X, in this case, the alternating sign matrices. But I would like them to have two different properties so that I can compute traces in these bases two different ways. I'd like the first basis, this V sub X basis, to be permuted by that cyclic group in exactly the way that the cyclic group permutes the set X. In other words, the basis element indexed by little x is sent to the basis element indexed by C of X. Okay? The other basis, I would like to diagonalize the action of the cyclic group. So this, what I call the W of X basis. I would like the cyclic group to scale the WX basis. So the generator of the cyclic group C takes WX to some root of unity zeta to some statistic on X times that basis element WX. So they're eigenvectors. And it's a cyclic group, so this has to be acting by roots of unity, so they're powers of that primitive root of unity zeta. But I would like this statistic on X to actually be a statistic which gives me a Q generating function for the set X. In other words, I'd like X of Q to be the Q count of the set X with respect to that statistic that predicted the eigenvalues. If that's the case, then I claim you now do the trace computation of one of your elements in the cyclic group, C to the D, and its trace on V should be computable using either basis, the V of X basis or the WX basis, and you should get the same answer. If you use the V of X basis, you're going to get the number of elements that are fixed by C to the D. You write down the permutation matrix, and the trace of a permutation matrix is the number of diagonal entries. It's the number of things that permutation fixes. So it's an easy calculation. Versus when you use this eigenvector basis, well, you should be summing up the eigenvalues. So you should be summing up zeta to the D raised to the statistic X over all these basis elements. And that's basically your Q analog evaluated at Q is zeta to the D at the root of unity. So if you can just somehow magically produce these bases, you're in business. It's easy, right? But unfortunately, we don't know how to do it all the time. Any questions about that desired proof that we would love to have in all cases?
So not about the desired proof, but if you check your chat, there's a question from the audience.
How do I check my chat?
I'll read it. It just says, somebody asked if you get cyclic sieving for the full dihedral group acting on the ASMs.
Yeah, that's a great question. So part of the problem with when you have dihedral, it's not clear what root of unity or what I should be plugging in to X of Q to model the number of fixed points for, say, the reflections in the dihedral group. We have things that seem like candidates, but I haven't quite phrased to my satisfaction a dihedral sieving phenomenon. We actually had some REU students 2 summers ago who came up with a reasonable notion of what dihedral sieving might mean, but it wasn't exactly just plugging in roots of unity. So let me push that question off to this REU report that I could send you a link to try and answer what I think of as dihedral sieving. Other questions? Okay, I stop annotating. Right, so here's, and I'm sorry, I'm a big complainer. I love to fetch. So what's even worse in the alternating sign matrix situation is that we don't even have a statistic, stat of X for X is an alternating sign matrix, which correctly models that Q generating function. That Q generating function, X of Q, that Stanton was working with, we knew that it was a polynomial in Q, even with non-negative coefficients, because it was the Q generating function for some other objects, this descending plane partitions. So Andrews in 1979 had introduced these objects called descending plane partitions pi with parts less than or equal to n. And these are plane partitions of some kind. I won't even get into the definition. It's slightly complicated. But when you sum up their entries, that's the weight of the partition. And if you Q count them according to that statistic, you get the X of Q that Stanton was working with. So we knew it was a polynomial in Q for something, but not, it was a generating function for something, but it was not a Q generating function for statistics on alternating sign matrices. And as far as I know, that's a frustrating question for experts in that area still. So this is part of the problem. Okay, enough kvetching. I'm about to move on to another example. Questions? Yes. I can't read that. Oh, yes, I could if I actually clicked on it. Chat. Didn't show up. Joanne, can you read it?
Sorry, just a sec. Yes. So the question was an easier question. If you restrict to ASMs with no -1s, that is permutation matrices, is there a Q analog of n factorial that produces cyclic sieving for the 90-degree rotation?
I believe the answer to that one is yes. I believe it's even better than that. I think we can even get a larger cyclic group that contains that cyclic group of order 4. And I think it comes from the Maj minus exceedance polynomial that was looked at by Sagan, Schreshin, and Wax. But I would have to check on that. I believe the answer is yes. Were there 2 questions? Maybe not.
That was the only one that came through just then.
Okay, good. Let's annoy you with another old example. So this is one from our original paper. It sure looks fun, and yet again, we understand it somehow the wrong way. Here's a triple that exhibits the cyclic sieving phenomenon. The set X is going to be triangulations of an n plus 2-sided polygon. So I've drawn an example with n equals 6. It's an octagon, 8 sides. And we act by the obvious cyclic group, which is just rotation. You rotate the polygon, it rotates the triangulation. These are triangulations which don't introduce any internal vertices. They only use vertices around the boundary. And my Q analog X of Q is McMahon's Q-Catalan polynomial. It's 1 over n plus 1 sub q is our same Q analog from before. And this 2n choose n sub q is a Q binomial coefficient, where in general, Q binomial coefficient n choose k sub q is n factorial sub q divided by k factorial sub q divided by n minus k factorial sub q. Okay, and so yes, this will exhibit a cyclic sieving phenomenon, and let me stop annotating so I can advance the page. And so I've just illustrated it here, what's going on when you have the hexagon. So this would be n equals 4. It is a cyclic group of order 6. So you have to plug in 6th roots of unity into this polynomial that you see there, which is, getting reasonably large. And you shouldn't be too surprised that if you plug in q equals 1, which is zeta to the 0, you're going to get 14, the Catalan number, which counts all of these triangulations. But if you plug in q equals -1, which is zeta cubed, you're going to get the ones which are fixed under doing the rotation, the smallest rotation 3 times, which is 180-degree rotation, so 2-fold symmetry. So that's at q equals -1. And when you plug in q equals zeta squared, you're plugging in a root of unity that has order 3. You get the ones that are, the ones that have order 3. You're plugging in a root of unity that has order 3, and you're counting these 2 triangulations which have symmetry under order 3 rotation. Okay, and then you could also plug in zeta itself. There are no triangulations which are fixed under 6-fold rotation, under 2 pi over 6 rotation. Nobody's fixed, so you do get 0. Okay. And so it sure looks nice. I wish I understood it. We only know a brute force proof, the one that was in our original paper. And what's even more annoying about this one, and the reason I want to reach out to many of you, is that there are 2 ways in which this one needs a cluster algebra proof. We know so much more about cluster algebras than we did, in 2000 or 2004. And let me tell you one of the ways in which this one seems to generalize to clusters. So There are two Taiwanese mathematicians, Sen Peng Yo and Tongshan Fu, in 2006. They generalized this. And I'm going to say some words that are just to set up some numerology, but don't worry about these words. If you've never seen them, this is the subject of another virtual talk. I'm going to talk about a finite real reflection group W. You should be thinking the previous case was when W is the symmetric group. I need some numbers, the degrees of W, D1 less than or equal to D2 up to Dn. These are the degrees of the basic invariant polynomials when W acts on a polynomial ring. Don't worry about it if you've never seen that. You call the biggest degree, Dn, you call it H, the Coxeter number, and you'll always get a CSP triple, these guys checked, when you let X be the W clusters. So for people who know cluster algebra theory, there's the cluster fan. So these would be like the chambers in the cluster fan. If your real reflection group wasn't crystallographic, these would be Nathan Reading's chambers in his Cambrian fan. And there's a cyclic action in that setting that comes from Fomin and Zelevinsky's deformed Coxeter elements. So there's somebody hanging around there. I'm going to call it tau here. And it has order H plus 2, where H was that Coxeter number. It's a cyclic action of that order on these clusters. And there is an X of Q, which is called a WQ Catalan polynomial. Let me be pointing here. So this X of Q, which is some quotient of a bunch of Q numbers divided by a bunch of other Q numbers that came from those degrees in that H. You take the degrees on the bottom as Q numbers, you shift them up by H plus the degrees on the top. And this is some well-known, well-established by now Q analog of a Catalan number. It's a polynomial in Q always, and that's not an obvious thing. And it will always do a more general CSP, like the polygon triangulations. So that means there should be a cluster proof, but we don't have one. So get on it. And here's another one that suggests there should be a cluster proof. There is a tantalizingly close, but not quite the same CSP that was proved by Brendan Rhodes in 2010. Here, instead of polygon triangulations, we do multi-dissections using a fixed number of edges, k edges. So what do I mean by that? Now I'm just going to use an n-gon, not an n plus 2 gon. So I've drawn a picture here with n equals 8. So there's an octagon underlying this story. And k is 13. 13 is the number of edges you see here counted with multiplicity. There should be, you're allowed to have multiple copies of the edges of, which are boundary edges or diagonals across the middle in this n-gon. And you just don't want them to be crossing each other so that they dissect the n-gon. But you don't have to use an edge. You might have missed some edges, like this boundary edge here. That's okay. But you fix the number of edges. You look at the number of multi-dissections with that fixed number of edges. You still let the cyclic group be the same rotations. And then there's a Q analog, which again has a product formula, but I've written it here as a principally specialized Schur function for the shape, which is 2 by k, a rectangular 2 by k. These are actually something pretty close to Q Catalans. They're called the Q Nariana polynomials. And I could have written down a product formula, but I didn't bother to do that. Here, Rhodes was able to prove it using that trace comparison. So what he comes up with is a model for a vector space. In this case, the vector space is the kth graded component of the coordinate ring of the Grassmannian of two planes in n space. It's well known that that thing has a cluster monomial basis. So cluster theory, this is one of the first examples of an important cluster algebra, is exactly this coordinate ring. So if you look at the cluster monomials of degree k, they give you one basis that's permuted by some element that Rhodes writes down. And then on the other hand, there's an eigenvector basis, a weight basis, which would be just any of our usual semi-standard tableau bases for these coordinate rings, which are realizing the irreducible representations of GL2C. So there's some fancy stuff going on there, but don't worry about it. The point is, this seems so close, and it has a good proof, and it involves clusters, and yet neither I nor Brendan nor anybody that I've talked to knows how to deduce the original one from this one. So please tell me how to do that. Any questions from those of you who are going to tell me how to do that? All right. You weren't fast enough. We're moving on.
Yeah, the silence is overwhelming, and it's not because I
Exactly.
left the mics muted.
Very good. Okay, I need to tell you about an old example with a new twist. So this is one that, sorry?
I can speak now? Okay.
Is-
Vic,
Was there
can you
somebody
hear me?
with a question?
Can you hear me? Yeah.
Yes.
Yes.
My question is, you mentioned the phenomenon for the triangulation of the n-gon.
Yes.
Do you have results for other Catalan objects? Like dig paths or something like this?
Yeah. And so, yes. So, Eli, there's also the one that has to do with standard Young tableau of 2 by n shape. And that's,
What is the action in that case?
yeah, so if I say it as 2 by n standard tableau, the action would be promotion. But on dict paths, I think that it essentially ends up being like a rotation. So, or certainly if we do non-crossing matchings of 2 endpoints around a circle, it corresponds to rotating the 2 endpoints. So there are
there is
definitely some other
canonical way to. So is there any canonical way to pass from one Catalan object to the other?
Not that I'm aware.
One of the bijections?
Yeah, only a few of them. I don't think there's any canonical way. I think in certain specific cases there are ways to do it, but not in general.
Okay, so every case is interesting by itself.
I think so.
Thank you.
Okay. All right. Let's try something old with a new twist. I want to rethink that McMahon Q Catalan. So let me point to it here. Excuse me. Instead of the formula that I originally gave to you, 1 over n plus 1, 2n choose n with q's on it, you can rewrite it. There's a standard way to rewrite the Catalan as 1 over 2n plus 1, 2n plus 1 choose n. And you can stick q's on it and it still works. It's a valid rewriting. And then one sees that it's a special case of something that's been considered recently quite a bit, these rational Q Catalans. So if you look at a and b being positive integers that are relatively prime, then 1 over a plus b sub q times a plus b choose a sub q, that turns out to be a polynomial in Q called a rational Q Catalan number, the AB Q Catalan number. And it's been considered by many people, by Drew Armstrong, Brendan Rhodes, Nathan Williams, Armstrong, Nick Lohr, Greg Warrington, and also Michelle Bodnar and Brendan Rhodes, and other people have looked at its properties. And when it does generalize the McMahon Q Catalan when you take A to be n and B to be n plus 1. Certainly those are relatively prime, and you can check, it'll go back. But more generally, what one can do is for any composition, alpha, this says alpha is alpha 1, alpha 2 up through alpha L. So those are positive integers, and I want them to be a composition of the number n. So they sum to the number n. If their parts are relatively prime, if the GCD of the parts of alpha is 1, then it's not too hard to check again, and I'm going to be giving you an argument for this, that what I'm calling C alpha sub q. So it's 1 over n sub q, and then the multinomial, q multinomial, n choose alpha. So that's 1 over n sub q, n choose alpha 1, alpha 2 up through alpha L sub q. And this is just defined with the factorial sub q in the usual way you would expect. It's the obvious way to qify. This thing turns out to have to be a polynomial in Q with integer coefficients, in fact, with non-negative integer coefficients. But let me tell you one way that we knew that it was a polynomial in Q. Whoops, stop annotating. Okay. So why is this thing a polynomial in Q? Well, it's because if I just took the Q multinomial, x of q to be the n choose alpha 1, alpha 2, ... That thing was part of a CSP that was in the original paper that we wrote with the Dennises. So there, that X sub Q, the Q multinomial, was one of our first examples. It was counting at Q equals 1, it counts words that have alpha 1 1s, alpha 2 2s, alpha 3 3s, etc. So words of length n, in which alpha I tells you how many times you use the letter I. So if you like, it's multiset permutations with a fixed multiplicities alpha on your elements of the multiset. Then you have a cyclic action of z mod nz, where n was the length of the word, the total number of letters. So the number that alpha was the composition of, just cycling positions. So you take your words and I've written it here, you take the word W1, W2 up to Wn, and you move the last letter to the beginning and shift everybody over by 1. So you cycle the words. And so we proved that in general, this triple, that set X, that cyclic group, and this Q analog, this multinomial coefficient, would give a CSP always, whether or not the GCD condition was there. That was irrelevant. But when the GCD condition is there, if the parts of alpha are 1, it's not too hard to see you can't have any words with symmetry. No words can have cyclic symmetry because the letters would have to be equally distributed, and the GCD of the letter multiplicities is 1. So if you think about it, this cyclic group action is free. And since there was a CSP, that means that a bunch of root of unity evaluations for that multinomial coefficient, it must vanish when you plug in any nth root of unity, which is not 1. So at Q equals 1, it gives you a multinomial coefficient as a number. But for all the other nth roots of unity, it has to vanish, which means it's divisible by the product of Q minus all the other nth roots of unity. And that's n sub Q. It's the thing that we were trying to show the divisibility of. Okay, so that was an argument using a CSP for why this thing was a polynomial in Q. And now I'm going to tell you that this thing does some cyclic sieving still after you divide. Oh, before I do that, I have to tell you what objects. Okay, so after you divide by n, I claim if we have our GCD condition, then the C alpha sub Q should be counting the C orbits, right? I said it was a free action of a group of size n, so the number of orbits should be obtained by taking the size of the set, dividing by n. So 1 over n, and then the multinomial n choose alpha, is counting the alpha necklaces. Necklaces would be cyclic orbits for your z mod nz cycling the words. I've shown an example here. Let me be pointing at it, in which alpha is 3, 4. I should have made that a red 3 and a blue 4. So when I take my words that have 3 red letters and 4 blue letters, and I look at their cyclic equivalence classes, I'm going to call those 3, 4 necklaces. Okay, alpha necklaces, 3 reds, 4 blues. And there should be 1 over 7, 7 choose 3 of them, because I began with 7 choose 3 words, and I just divided by 7 because it was a free action of a cyclic group of size 7. Okay? And that's going to be my set X, is the necklaces. So we're going to get, oh yes, I need to tell you some group that's acting on the necklaces. It looks like I got rid of the cyclic group action. What kind of a cyclic group should be acting? Well, now it's the reflection that somebody brought up earlier. So what's true is you still have on your necklaces, oop, I did the wrong thing. On your necklaces, you still have the ability to reflect a necklace across any symmetry line. And it gives you another necklace. And sometimes you go back to the same necklace because the necklace already had a reflection symmetry. And sometimes you're not fixed. You have an orbit of size 2. So this is a situation where you might ask for a Q equals -1 phenomenon. And indeed there is one. So my current student, Eric Stuckey, he recently proved that whenever the GCD of the alphas is 1, you get a Q equals -1 phenomenon for these alpha necklaces with this order 2 action of reflection by tau that I'm showing you, and where the y sub q is this generalization of the q Catalan number and the rational q Catalan number, this 1 over n sub q, n choose alpha sub q. And this one has an interesting proof, and it generalizes. So let me say what's interesting here. Oh, before I do that, do an example. So in our case, we had these 5 necklaces, They had some non-trivial tau actions. Some of them were acted on trivially. And here's my 1 over 7 sub q, 7 choose 3 sub q. This is actually a Q Catalan. This is one of these Catalan cases. This is the Q Catalan that at Q equals 1 gives us back 5, the size of the set. But here at Q equals -1, you can see you'll get 3 is your evaluation. And so it's counting the 3 of them that were fixed, the 3 necklaces that had reflection symmetry. Okay? Questions on that? All right, let me advance. Oops, stop annotating. So the proof that Eric Stuckey gives is interesting. It uses Moline's theorem from invariant theory, okay, which is some way of writing down Hilbert series for invariant rings when finite groups act on polynomials. And the reason this comes up is because it's not just about necklaces. It generalizes quite a bit further. So I told you a story in which we began with these alpha words that had a fixed number of letters of each color. And we put on this GCD condition so that the cyclic group would act freely. And then we got this Q equals -1 phenomenon when we took the C orbits, the set Y, which was the alpha necklaces. So the way this generalizes is the alpha words turn into more generally cosets of the symmetric group Sn by a subgroup H, such that the action of the n cycle on the other side of the cosets. So these are cosets where H is on the right. You let the cyclic group generated by an n cycle act on the left. And if that action is free, then we know how to write down a Q analog of X that will be divisible by n sub Q, because we know of a CSP in that situation. We divide by the n sub Q and we get a CSP now, or Stuckey proves a CSP for the double cosets. So the C orbits of the cosets that have H on the right. And the leftover action, the thing that plays the role of tau, is elements in the symmetric group that normalize the n cycle. So things which are in the normalizer of the permutation, 1 goes to 2 goes to n goes to 1. So I like this one. It's not exactly a trace comparison proof, although it's related, and it's quite interesting. I think what I'm going to do is not tell you about this other new one, which Theo Divropoulos talked about at FIPSAC last year. If you want to hear about it, I love it a lot. I really like it. But you could go to the FIPSAC 2017 abstract and look up Divropoulos. I believe that would be the longest Greek name you're going to find in the list of authors. And so I'll stop there. Thanks.
Okay, so you're allowed to unmute to applaud. So,
Yeah.
but anyhow, thank you very much. And in general, feel free to unmute and turn your videos on. We can chat a little bit, talk to Vic, and see if there's any questions.
Yeah, questions?
I'm hearing something. Okay, you got to speak up a little bit, though.
Well, I as a non-expert, I'm wondering what's special about the cyclic group. I see that you have some ideas that the hedral group might also allow for some kind of counting trick like this. What about a product of cyclic groups, or something also quite an abelian group? Let's say a finite abelian group.
Right. So definitely for finite abelian groups, we know what we want, and there are good examples around. So one of the papers where we wrote about this is with Hélène Barcelot and Dennis Stanton. It's called bi-Mahonian distributions. And there we had a bicyclic sieving phenomenon, which was a product of 2 cyclic groups, Bill. And then there's been others. So for example, Andy Berget and Jia Huang have a paper in which they look at a direct product of cyclic groups, so a finite abelian group. They find some interesting examples. And so definitely for finite abelian groups, we know exactly what we want to happen, and there are some interesting examples.
Thank you.
Do you have any other questions for for Vic this evening? No? All right. Well, Bill, you there? We're set with the recording?
I'll stop recording.
Well, or, yeah. So, well, anyhow, thank you all very much. Keep your eye out for further talks. But let's thank Vic again for this really great one. Thank you, Vic. If there's anyone who is not getting these announcements, shoot me an email, or Seth Chaikin has the distribution list for this, and we also try to get them up on Greg West's clearinghouse for conference announcements. Yeah. Okay, hold on. Let me put in, somebody just asked this. Let me just put the email for Seth to get added to the distribution list. Let me send this to everybody in the chat.